I'm Dan Fry. I'm a teacher at MIT in Cambridge, Massachusetts, and today we're going to do a session about design of mechanisms. This should be a fun session that allows you to get hands-on and to think hard about how machines work. This is a session that's going to rely upon your knowledge of geometry, particularly facts about circles and triangles. It turns out that this topic of geometry is related to something called kinematics that we engineers use. Kinematics is just geometry in motion. So you're going to use geometry in ways that might be a little bit different than what you're used to, but it shouldn't intimidate you because we're going to have hardware that's available so that you can gain some experience and some insight into how it works. Let me define a couple terms before I move on. Design and mechanism. Design is the process of creating an artifact that executes some useful function. This is one of my favorite topics because it allows me as an engineer to be creative and to make things that have never been seen before. So that's design. Now, what's a mechanism? A mechanism is a collection of items, parts, that are interconnected so that their motions are coordinated. So design of mechanisms involves choosing the shapes and locations of those parts and the way they're interconnected so that you get the function that you're interested in creating. Now, mechanisms are all around us. For example, in agriculture, a mechanism might be used in crop processing to pick a vegetable or to take the husk off of that same vegetable. Also, a mechanism might be used in a sewing machine to guide a needle and thread and make a stitch. Another very common use of mechanisms is in engines. Here on the computer screen, we have a model of a compressed air engine, and it's all color-coded so that we can talk about the pieces and keep track of all the moving parts. Let me start with this red piece here on the left. That's what I call a crankshaft. The red piece is mounted up in the case of the engine on a bearing here, so it can rotate about this point right at the center. Let me cause that rotation now by dragging on it. See the rotation of the red part of the crankshaft? All right, now let me talk about this pin here. This is called the crank pin. This crank pin is all part of one rigid component called the crankshaft. Therefore, the distance between the center of this pin and this bearing here, the center of the crankshaft, is fixed. So what happens when you have a collection of points which are all one fixed distance from a single fixed point? Well, that's a circle. You know that from geometry. So this configuration of parts allows the pin to move, but only in a circle. Now let's go to the other components of the mechanism. Here in blue is a connecting rod. As the name suggests, it connects. It connects between this point here, the center of the crank pin, over to the piston, this green part on the right. Now again, the connecting rod is rigid, so the distance between the center of the crank pin and the center of this bearing over here that connects it to the piston is also a fixed length. Finally, we have the piston, which is in green. And the piston is a cylinder, and it's inside of a hole that fits closely to that cylinder, so it can just slide back and forth. So what does the mechanism do? It converts the sliding back and forth motion of the piston through the connecting rod into rotary motion of the crankshaft. So this particular mechanism changes one kind of motion, back and forth motion, into another kind of motion, around and around cranking of the crankshaft. Now I want to give you an exercise. What if I told you some facts about the geometry of this mechanism? What if it turned out that the distance between the center of the crankshaft and the center of the crank pin was 3 units, let's say 3 millimeters? Then I also told you that the length of the connecting rod Therefore, the distance from this point to this point is 5 millimeters. And finally, what if I place the piston so that the distance from the center of this joint, which connects the connecting rod and the piston, to this point, which is the center of the crankshaft, is 4 millimeters. So, to review, from here to here, 3 millimeters. From here to here, 5 millimeters. From here to here, 4 millimeters around in the circuit. Now, the challenge for you is, given those facts of what you know about geometry, can you figure out what location and what angle the connecting rod has to have with respect to the rest of the engine, in particular the case? So what you've just seen is that geometry can be used to understand the relationship among moving parts in a mechanism. Geometry is the mathematics that allows you to see the interrelationships. But it's also important to get a physical intuition. So I want you to also work with an actual prototype of a mechanism. I have something here in the room that I made out of pegboard. It's going to be very similar to the mechanism we just saw in the engine. Now you should create something similar to this, either out of pegboard, if that's available to you where you are, or perhaps out of construction paper and thumbtacks, or maybe cardboard and nails, whatever works for you. Now, this mechanism I put on the pegboard is one of a class of mechanisms called a 4-bar mechanism. Let me go through the 4 bars now. This yellow bar is stationary. It's really just a piece of construction paper that I've taped to the pegboard. Now, there are 2 other bars that are pinned to the pegboard using bolts, so they can move around in circles, like this. The 4th bar is a piece of pegboard that is pinned to the ends of the other 2, the red one here and the green one here, pinned at the ends. Exactly how you make those joints is not important. The key thing is that they have to allow rotation, but as before, they make sure that the distances between the different points are fixed and therefore that they move in circles. So for example, this component here makes sure that the distance to this pin is always on a circle of 1, 2, 3, 4 units on the pegboard. Now here's the challenge for you. What would happen if I grab the end of this red link and move it around in a circle? What will be the resulting motions of the green link? And what is the relationship of this mechanism to the one that we just explored? That is, the compressed air engine that was in the toy and that we also illustrated on the computer screen. Take that as an exercise. Work with a physical prototype. You and the other students in the room and your instructor have been building actual physical prototypes that show how mechanisms work. And what you've seen is that one of the things you can do is make a 4-bar mechanism that converts rotary motion into essentially oscillating motion. What we have here is the red link. If it goes around and around, the farthest end of the green link essentially just goes back and forth. Now, if we're being precise, it's moving in a circle centered at this location, but the number of degrees in the arc are so short, are so few, that it's essentially a straight line motion to engineering approximation. So, now, when we as engineers take a mechanism that's of a particular fixed arrangement that already exists, such as what we saw in the compressed air engine, and we use our analytical skills of math and physics to figure out what it will do, we call that analysis. You've got what exists, and you try to figure out how it'll behave. But engineers also need to do synthesis. That is, sometimes they know how we want something to behave, and we have to figure out what configuration will bring that about. So, let's do a little bit of synthesis now. I'm going to move the pegboard out of the way, and we're going to use a little different piece of pegboard. I've cut out a piece of pegboard into what looks to me like the bed of a dump truck. What you imagine is that this is the part that holds material such as gravel. And what we're going to do is we're going to come up with a specification for how this dump truck should operate. We're going to define some positions that indicate how it should behave when we apply some energy to it and make it operate. So let's first depict the normal position of the bed when it's low and flat and we drive the dump truck around on a construction site. I'm going to try to make it as flat as I can, and I'm going to trace it out. This represents on the chalkboard one of the desired positions of the bed of a dump truck. Now, what I have to show you is some motions that we want the dump truck to take. Now, let's imagine that what we want it to do first is to move up and over, for example, to get over a barrier. So, let's say that we want it to move up by 8 units and over by 4. So we count them out. 1, 2, 3, 4, 5, 6, 7, 8, and over 1, 2, 3, 4, and we make a mark. And then we move the bed over to that mark. Line it up and make it as flat as we can make it by eye. If we were working in a CAD tool, we could make it exactly flat. I'm going to trace it out. So what we're imagining is we want to lift the truck up, keeping it relatively flat. So, for example, we can go over, maybe there's an obstacle there, and we want to get over that. Now, in the last part of the motion, what we want it to do is to come over further and dump out. So let's say we want it to go up 6 units, 6, and over 14 units, 6, 7, 8, 9, 10, 11, 12, 13, 14. Make a mark. Lift this up. Move it over to that mark. And also, let's say that what we want it to do at that point is to dump out. So, that's our last position. We want it to move up and over. Actually, I want it, let's say that the obstacle is a little smaller than what I had envisioned. It's just there. So, what we have is 3 specified positions of the bed of a dump truck. We want to pick that bed up, keeping it relatively flat to overcome an obstacle, then move it up and over, and turn it so that the gravel or whatever else we're carrying dumps out. So what we've done is with some precision to define what we want the mechanism to do, the motions through which we want the mechanism to guide the bed. Now, if we want to guide this motion using a 4-bar mechanism, consider what we need to do. We know that a 4-bar mechanism has 2 links that connect from what we'll call the ground to something that moves. So, the bed is that something that moves, and we want to figure out where the links on the ground go. So we have to come up with the locations of 2 joints at either end of that link. Now, let's assume that on this bed, that the first joint goes here. that would be a convenient place to locate a joint that is at the end of one of the lengths of the 4-bar mechanism. Now, if we place the joint there, then when the bed lifts up over into this position, that point is in the same relative position. The same distance up from this corner, the same distance over from this corner. It's really the same physical point, but it's at a different location in space because of the motion of the bed in time. Now, in the third position, again, the bearing moves to here. Again, the same relative position, but with reference to the ground upon which we're driving the dump truck, it has moved, but with respect to the bed itself, it has not. It's at the same relative location. Now what we have is 3 points in space that define different locations of the bearing at different points in time. And we've decided that we're going to execute this motion with a 4-bar mechanism, meaning that the motions of this bearing are going to be guided by some kind of rigid link that's connected somewhere to our truck itself, which is, we'll assume, stationary. So how can we reason out the location of the stationary joint from 3 positions of the moving joint? That is the question that I pose to you. And what I'd like you to do now is to take another pause from the videotape, work with the students in the room and your instructor, and work out how you'll do that. Take 3 positions of something moving and reason out the position of the fixed point. Okay, you've been hard at work synthesizing a mechanism, and I've been working on the same problem right here. So remember, you had these 3 points that represented locations of a pinned joint on the bed of your dump truck, and you were trying to figure out where that stationary joint needed to be. That is, where the center of a circle was that included all those 3 points. You've been working on that, and I've been working on it too, here on the board. Now, there are multiple ways to do this, but I'm going to sketch out one relatively easy way. I took 2 of the points on the right side of the mechanism, and I connected them with a line segment. Then I found the middle of that line segment. So this segment of the line above it is the same length as this segment of the line below it. Then I constructed, with a square piece of paper, in this case, another line that's perpendicular and goes through the midpoint of that segment, and that extends out in this direction. Now, what I know is that my joint, the center of the circle I need, is somewhere along that line. But I want it down to a single point, so I know just where to put the bearing on the bed of my truck. So I take 2 other points from the set of 3. I construct a line segment between those 2 and find the midpoint again and run a perpendicular down, and I find the point where they intersect. You see, I know that the center of that circle needs to be on this line, and the center of that circle also needs to be on this line. The only point that obeys those 2 constraints simultaneously is this point at the intersection. So that is the center of my circle, which contains these 3 points on the desired specified positions of my dump truck bed. That point I found, if I take a ruler, is just 4 units over to the left of the bottom left corner of my dump truck, and it's 5 units on the pegboard, or whatever you prefer, up from this point at the corner of the dump truck. So 4 and 5. So that's half of our 4-bar mechanism. Now I have to take the exact same process and apply it to the left half. So here I pick another point on the bed of the truck. Again, a convenient point, just the bottom left-hand side. Here I've marked it and circled it. That would move up to this position in the second desired location of the bed. And finally, it would end up in this position at the third location of the bed when it's dumping out. Again, those 3 points define one circle, a unique circle with one center and one radius. Using, again, the same geometric construction technique, I could find the center of that circle, and I would find that it's aligned with the one before, and it's 8 units up above it. 8 units on my pegboard, or 8 units in whatever scheme you're using there, in construction paper and pins, or whatever medium you're using. So I claim that we have now synthesized a 4-bar mechanism that will do 3-position synthesis. Let me show you that that's the case by building it out of a pegboard. I've done the work ahead, and here's the result. I've got a pegboard here, and it has a link in one of the specified positions going to the left corner of my dump truck, another link 8 units below it, and that's extending over to the right bottom corner of my dump truck, and I've color-coded it just the same way as our previous mechanism. So we've got a long green link, a moving blue link, and a short red link. Now, let's see it move. We start at one position, which is basically flat. It then moves up into another position, which is also basically flat, and you can see the correspondence between what I put on the board and that second position. Now, it moves yet again, over and down, and you see it again corresponds to the position that we specified. It moved over and dumped out. Also, interesting to note that it went over the obstacle that we had defined before. Started in the first position, missing the obstacle. Up to the second position, the bed missing the obstacle. Into the third position, again avoiding the obstacle. But you'll see one problem. Although the bed that contained the gravel avoided the obstacle, look what happens to the red link. The red link goes right over it like that. So what we have to do is come up with a way to change the design and avoid that obstacle. So that is the next challenge for you. The task that I'm giving you is think of a few different options. What can you do to change the design of this mechanism so it still has the desired motions, but won't have this interference between the obstacle and the red link? There are more than one way to do it, so try to come up with a few different options, work together with the other students in the room and your instructor, try to be creative,